Okay, we are live. Good morning, everyone. I'm Archana Gupta and your host for the session. Welcome to today's exciting hands on machine learning workshop. We are thrilled to have an incredible speaker with us today, Mr. Akshay Gautam. He's a Chief Technology Officer at Fern Bio. He's here to guide us through the practical world of machine learning. So get ready to learn, build, and explore. Over to you, sir.
Thank you, Archana. Uh, as Archana introduced me, my name is Akshay Gautam. I've been building in machine learning since before AI thing became a popular thing. I used to do traditional machine learning, right? Linear regression, residual regression, stuff like that, XGBoost. And then now I work as a CTO for a company based in the US, and we serve for like bigger clients like Qualcomm and Google. This this session, I'll cover some topics such as feature engineering and feature selection, as well as bias variance trade-off. I decided to go with these topics because feature engineering and feature selection, these two topics are like really important. It can, and this comes from personal experience, it can completely change the course of your work or your project or whatever you're doing. For example, there was a I always reference this because it's one of the biggest things that happened in that year for me. I was part of a Kaggle competition where we were supposed to do Boston housing price prediction, right? And back in the day, or I don't know if it is common knowledge today, but back in the day, everybody knew that for tabular data, you were just supposed to use boosting algorithms like XGBoost and LightGBM, right? And it will just perform better than every other algorithm out there. At the time, I was still learning machine learning. This is 2019, 2020, right? So I thought, okay, let's see, let's go, let's try something. I was learning regularized linear models, right? So linear regression, but with regularization, like ridge regression and lasso regression, stuff like that. I tried to use linear regression to beat uh, XGBoost. So for those who don't have any context, this is funny. This is very funny. It's like trying to outrace a train with a cycle, right? I did try this. I knew this nothing will come out of it, but I was trying this, and as I was trying this, I realized that the features of the data set were extremely correlated, but were extremely sparse, right? They were far apart, but they also had correlation in them. So I thought, if what if I do a lot of feature engineering with this data? And I got into the feature engineering. I got lost in it. I love feature engineering. It's fun, right? I got lost in it, and at the end of the day, when I was done with all of it, when I opened the dashboard, I was ranked one in the competition. Ranked one, right? It was unheard of. A linear regression model beating XGBoost was unheard of at the time, right? It is a rolling competition. I think it's still running. Rolling competition means every week they select a new leaderboard, and things have progressed a lot more since then. But it was eye-opening moment for me. I realized how much features help you, right? That was also the moment I realized that machine learning in any form, be it traditional machine learning, be it transformers based AI, it's all garbage in, garbage out. Which means if your data is good, your output will be good. Your models are not going to make that much of a difference, right? With all of this backstory in our mind, uh, let's get to the topics, right? I would try to share my screen. I have a Notion document ready just to reference stuff, right? Just for the reference, I would not be sharing this Notion document with anybody. So if you are, watching this, take notes along the way. I never share stuff with workshop participants. It's a way to keep focus to a maximum, right? Also, if you take notes, notes are always your interpretation of something. So how you have interpreted something is how you will take notes, which is again, uh, in my opinion, the best way to learn, right? So can you see my screen?
Yeah, one second.
Right.
Yeah, great.
So uh, We'll be talking about feature engineering and feature selection. So I'll get right into it. Right. Let's talk about feature engineering. So what is feature engineering? It's I mean it has engineering and it has features. So we have kind of an idea like okay we are working with features, but what is feature engineering? It's it's like let's say you have a lot of features about something. You have let's talk about the housing price prediction, right? You have a house. You have data about how many rooms it has, how many kitchen it has, how many washrooms it has, right? Everything. How many square footage area it has, how many uh, when was it built, right? Where is it located, right? That is called features, right? Of that specific home, that specific data point. If I were to now think about how different models would interpret the data, for example, let's talk about KNN, right? Uh, KNN would want some distance metric to work with. Uh, in our in our feature, we don't directly have any distance metric, right? We do not have any distance metric. We have where it's located. So now what we can do is we can calculate because we know where it's located. We can calculate the distance of that particular home from the city center, right? So for every home now we have another distance metric. How far away is it from city center? Which will affect the house's price. If it is closer to the city center, it will be costlier. If it is far away, it will be less costly comparatively, right? This thing where we looked at features, we transformed it to help ourselves. It is called feature engineering, right? It's a simple process. The thing with feature engineering is you have to know for it to work. Like if you don't know what you are trying to get out of it, it'll never work. You cannot throw stones in an empty void and expect it to make noise, right? You have to know what you're trying to hit, and that's where this whole thing will show its magic, right? This is a creative step. So, for example, algorithms like decision tree, which we'll talk about in I think the next session, decision tree, KNN, SVM, these all learn based on meaningful features. So, for example, if their features have meaningful correlation, then only these algorithms will show its power and work well, right? It's not like neural networks where you just put all the data and you let the neural network worry about the connections, right? So the question is why, right? Like why do it? I mean, you have an intuition of why do it, but the thing is, without feature engineering, these models will either suffer from high bias, right, which is basically underfitting, and this also we'll discuss later, or high variance, which is overfitting, right, disrupting the bias variance trade-off. And this feature engineering step is necessary to bridge the gap between what the algorithm wants, because every algorithm requires a different type of data, right? And feature engineering helps us to create that data from real world data. Real world data is messy. It's messy, it's not right, it's almost never suitable for any one type of algorithm. In fact, in the age of AI, where we have transformers models which are powerful and they can, extract features from unseen data, even today we have to do a lot of feature engineering, right? Even in the age of AI. So it's a very important step, and it's very necessary to bridge the gap between the real world data that we obtain today and the algorithm necessities, what it needs, in which form it needs, right? What are some common ways to do it? Some common ways are one hot encoding. One hot encoding is basically you take one feature and you encode that one feature and everything else is treated as another feature. So let's say you have 16 features. You have house, how many number of rooms are there, where it's located, or you have discrete features like, is there a lot of sunlight or no sunlight, right? Is the house multi-floored or a single floor? Things like that, right? What you can do is you can treat one feature as, let's say we encoded with like 0, 1, and the every other feature becomes 0, right? So one feature we treat as 1 and every other feature becomes 0. Similarly, we have like scaling and we have normalization. Scaling is, I'll give you an example. It's better that way. Let's consider linear regression with multiple polynomial, right? Like, uh, let's think about you have a data set with like a lot of features, but you have linear regression. So you have like, you can enter only one feature in the algorithm. In this case, what will happen is if your data is too far apart, for example, one of the numbers in the data is number of rooms. Number of rooms will be usually from 1 to 10, right? One room, three rooms, five rooms. If it's a huge mansion, it will have 10 rooms, right? But then you have a number called square footage, which will be in thousands, 1,000 square foot, 1,200 square foot. These two numbers are very far apart from each other, but these two are features. And for let's say logistic regression, or for let's say any algorithm with multiple feature inputs, if you input these features as it is, this is going to completely outscale your algorithm, because your algorithm does not know that these big numbers and these smaller numbers are not related directly. They are related, but indirectly, right? We need to scale this. All of these numbers need to be put in the similar scale of, let's say, 0 to 1, where you have 0.01, 0.1, 0.5, 0.9, right? Like that. The square footage also needs to be fit between 0 to 1, and the number of rooms also need to be scaled. It's to bring every other number in the similar range, to try to balance it so that the mathematical equations that you will use in these algorithms do not get disturbed by the large difference between these numbers. This is called scaling or normalization, right? Binning is another way. You just take multiple features, you combine them, you remove them. The one method that I want to focus on is domain informed feature construction. This is very important because it's one of the most, these are simpler methods. The ones I talked about, one hot encoding, scaling, normalization, binning. These are simpler methods you do in almost every algorithm, almost every type of data. Domain informed feature construction is where you will be differentiated uh, by somebody as an expert or a novice, or a beginner, right? Domain informed feature construction is basically you understand the domain the data comes from. Let's say it comes from housing price prediction. You understand real estate. Like how I talked about, let's calculate the distance of the home from the city center. That's informed feature construction. I knew that the distance from the city center will affect the housing pricing, right? And because I knew the domain, I created a new feature based on it. This feature did not exist before. I only had location data to work with, but I created this feature from my domain knowledge. And this is called domain informed feature construction. This has one of the highest ROIs. ROIs as in return of investment, return on investment, right? You take, let's say, 2 days or 3 days to do domain informed feature construction on real world data with like millions of rows. This will give you very, very good results if you have done it right, right? So just something I wanted to throw out there. Uh, any questions about feature engineering as of now?
Everyone, if you have a doubt, you can write it in chat. We'll take up in between the session.
Yeah,
So as of now, there is.
right. All right. Let's because in interest of time, I have to move fast. So feature selection. Feature selection is not that different from feature engineering, right? Uh, when I started this talk, I told you that there was a moment. There was actually one moment where I realized that machine learning is garbage in, garbage out, and this is the term garbage in phrase, garbage in, garbage out. This was coined by, I think, long ago by some IBM engineer. He was very famous. I'm sorry, I'm not good with names, but he coined this, and it's true for almost every type of system out there in IT. Even in the age of AI, if your model gets garbage data, no matter how much data, how much compute, how good an architecture you have, even if you have 300 billion parameters, it will still be a garbage model, right? So feature selection is where we fight garbage in, garbage out. How are they different though? We talked about feature engineering. How is feature selection different? Feature engineering is where we took the features that we had in data and we created new, we transformed it, we did all sorts of things to get as many features as we could, at least relevant ones. In feature selection, it's where we purge or increase it depending on how our algorithm wants to deal with it. So let's look at what it is, right? Feature selection is the technique of identifying and retaining only the most relevant features from the dataset, right? So what does this mean? As I talked before, we could create a feature, distance from city center, for housing price prediction, right? Will it be relevant in every scenario? It will be relevant in its price, yes. But will it be relevant in scenarios such as how popular it is among different age groups? Let's say we are trying to find how popular what type of housing is in different age group. Now, in this case, maybe this feature is not that important. And if we choose to include it, it will cause something called as introduce noise, right? And it's a very sneaky thing. Noise in your data is a very, very sneaky thing. It's very hard to find out and it's very hard to fight. But we'll talk about how we do that, right? It reduces, so feature selection reduces data complexity, focusing models on what matters. And again, not every model wants every feature. Certain type of model want certain types of features, right? If we don't do that, we provide every model every feature, you will be left with something below the par, something terrible, something completely, garbage in, garbage out type of model. So why do we even do it, right? Why do we even do it? So too many features might not be ideal for most scenarios, as irrelevant features will introduce noise, computation based, and even increase bias. Noise and computation based is something that, first of all, computation based, let's get done with it, right? Computation based, if you're rich, if you're OpenAI, if you're Google, you don't care about it. You have a lot of compute, you're GPU rich, right? Your algorithms can run day and night for months. So maybe you are Google and you're GPU rich, maybe your company has a lot of GPUs for you. You don't have to worry about computation, power going to waste. It's fine. Although I would suggest that every time you practice any form of software engineering related to software, try to practice efficiency. Efficiency always gives good results. But let's get done with it and go to noise. Noise, as I told, it's a very sneaky thing, right? It's a very sneaky thing. It's very hard to point out. It's very hard to figure out. Noise will be something like, did anybody see the recent thing that happened with Grok 4 by XAI, Elon Musk's model? It started pretending to be a very disliked figure from history, right? And it was giving like very bad comments, and it was very racist. Uh, it was basically it was a mess. It was a dumpster fire, right? That kind of stuff happens because your model has noise, which you did not find in time. Now, the scale of noise in this case was very large. The engineers missed it somehow because I think XCI does not do alignment steps, but that is very bad because noise does not make your model bad. It makes your model give the wrong outputs with very high confidence, and that is dangerous. If I'm here teaching you something wrong with high confidence, something like, oh, you should use neural networks on tabular data, that is wrong because now you will think, oh, this person is right. And you will try neural networks on tabular data, which is not good, right? So that is why noise is so dangerous. And the next part, which is uh, it increases bias, which is again very sneaky thing. I would give an example. This is a very sensitive topic, so take it as an educational thing, right? But let's say there's a workplace and there's data from a company about hiring and people who leave. Companies do not prefer candidates who will leave after 1 year or 2 years, right? They prefer candidates who will stay with the company through thick and thin. They have the data where their model, they fit the data on a model to try to find candidates who are more likely to stay in the company. Now the data finds the model finds out that women tend to leave the company more frequently. And what that would do is that would make the model bias against women. So the model will not hire women for that company. But what could be the reality? The reality could be that the workplace of that company is toxic to women, right? It's not right for women. So it's the other way around. It's not that women are not good employees. It's this company is not good to women and they're not treating women good, right? In this case, your model did a very bad bias. It's terrible, right? Imagine a model which you fit. And by the way, these kind of data is available publicly. So you have multiple companies that make their hiring data public. So even if you use public data, you have to be very careful. Maybe this one workplace has a lot of data on women leaving, and it's because this one workplace is toxic to women. But if you train your model with this and other data combined, your model will likely become biased against women in the workplace, right? We do not want that. We have to, go in feature selection and select the features. Okay, gender is irrelevant for this kind of a thing. Where if I'm hiring for a tech role, I don't want to look at somebody's gender. Like I have personally hired for my company, and I never ask for this stuff. I'll ask, oh, give me your work, project links. Tell me what you have built. I don't care about what your gender is or what your age is, right? That is how it should be. That is what feature selection is, trying to solve. So again, as I told, it feature selection chooses only relevant features based on what we want. So if I want to find out which candidate will be a good fit for my company, I would use, let's say, what skills they have, how many projects they have built, maybe years of experience even, right? But not gender and age and things like that. Those are irrelevant for us. What are the methods of feature engineering? The methods are filter. Filter is just filter. I mean, it's common. You have different types of filters. Let's say, for example, we are dealing with medical data, right? And we are dealing with some kind of model where we are dealing with pregnancy related stuff. Now, the first thing I will do is put a filter that men are not included in the data, because it'll be funny if our data is pregnancy data and men are there, right? So we have to take care of that. That is filter. And wrapper is a similar concept where what we do is we create a stencil. Basically, we create a stencil around the data to try and find what fits in the stencil and take it. Stencil as in an empty place, right? Like a socket to fill. So you take data from there, whichever is suitable for your model, and then we use that. Again, we have embeddings. Embedding is a very diverse topic. It's a single topic in its own right, honestly. But embedding is, let's say, where you take a data and you know what way we're supposed to. Okay, let me do this. You have color data. You have, again, going into the housing price prediction. You have color data for the houses. Now, my job as a data scientist or data analyst is to only deal with or find how black colored homes or white colored homes perform, right? But I don't care how yellow and green perform. So what I would do is I would select the white ones, and everything else will be treated something like one hot encoding. But like here, I would do feature selection where the data from, if we combine all of the remaining colors into one, it will completely bias our data, because then our model will think that white is a minority color or black is a minority color, and the other feature that we have, right? We have two now, white and others. So the others is now a majority feature and it will bias our data. We do not want that. So what we do is we'll carefully select, and we'll have, let's say, only two colors. Let's say white versus red, and then we will have white versus green, and then we will have white versus black, and then with each separate comparisons we will compare these numbers, take average, do whatever other computation we can do on this, right? That is the right way to deal with this kind of data, right? So this is very important. We have dimensionality reduction. Dimensionality reduction is a very important concept. This helps us deal with the curse of dimensionality. The curse of dimensionality is a it's an read about it, but it's basically that if you have data in higher dimensions, like n equals to 6 or n equals to 12 or even more, I have personally, when I was a data scientist back in the day, I have personally worked with data with 1,000, 1,200 dimensions, right? That kind of data is messy to deal with. It's a pain. It's a pain, right? That is called curse of dimensionality. And dimensionality reduction, there are algorithms like PCA, Principal Component Analytics. There is other algorithms to deal with it. These are tried. Let's say you have 6 dimension data, so PCA will try to reduce it to, let's say, 3 dimensions. The features which actually affect your outcome will still be there, right? Heuristics is a model based. So let's say you have a model which wants a specific type of data. You will make it vote. You will make it choose which type of data do you want, and you will see which type of data it performs better on. These are all you have. These are not all, by the way. There are more and more and more methods. There are hundreds of methods of these feature engineering and selection. These are some of the most common ones I'm talking about. I would encourage you, if you went ahead and read about this on your own using AI models or whatever you like to read about. Uh, so the bias variance trade-off, right? This is the bias variance trade-off. It has to be perfectly balanced, as all things should be, right? It has to be perfectly balanced. And before I go to explain bias variance trade-off and finding and trying to explain how it works, stuff like that, is there any question till now?
So yeah, there's a question by Ritika. What is the difference between supervised and unsupervised learning with real life examples?
I see. I see. Very, very simple. You want supervised learning and unsupervised learning. Supervised learning is where you already know the correct answer, right? And you train yourself to understand. For example, we when we were kids, we all have mugged up state and their capitals, right? When we did that, we were like, okay, or country and their capitals, right? So we were like, okay, India's New Delhi and USS Washington. There we were learning it. We already knew the question, which is the country, and its capital, which is Washington or New Delhi for India. Here we knew the answer and the question, and we were training ourselves to learn that. This is supervised learning. Unsupervised learning is where you figure out things where you don't know the answer, and you figure it out based on the data itself. For example, you have a mix of candies, right? A mix of candies. You have like a lot of mix of candies of different color. You'll just sit down and you will separate all the red ones to one side and all the green ones to one side. It's called clustering. So here you did not have any answer specific, like, okay, these are the red ones, and you just know that, okay, these are of one group in any one way, right? Here I used color, but it can be taste. Maybe you ate all the candies, right? And next time you buy them, you know how they taste, and maybe the red ones and the green ones taste the same. So next time you'll cluster the red ones and green ones together, and others together. That is unsupervised learning, where you don't know the answer, you don't know what you're going for, but you try to find patterns in the data and get them together to work with. So other questions, do we have other questions?
Yeah, we have one more question and by Pooja, and that is, can you explain wrapper and embedded again?
So okay, again, these are wrapper and embedded techniques are advanced techniques, right? I would suggest that you go and read about this on your own in detail, because I cannot cover all the nuances in this session. But just so you know, wrapper is where we take our data. Let's let's try to go for a real world example, right? Let's say that we have let's say we have a lot of let's say we are dealing with water filtration systems, right? And you have the pH value for the water can range in a very large range. It can be zero point 0.1 or 0. It's very nuanced. In this case, if you try to dealt with every single value as a discrete value as in its own entity, it'll be tough to deal with. It'll be very tough to deal with. What you do is you wrap the data. So you put this in a range, right? So you put this, okay, from pH 1 to 3 is not acceptable. pH 3 to 4 is fine, but pH again 4 to 7 is not acceptable, right? And when you do that, we don't have to give our model 1 to 3 in its discrete form because it's not necessary anyways, right? We don't need the data. We just know that it's not suitable for us humans. So why even deal with it, right? Now, maybe in this case, what we can do is we can deal with the values, discrete values between 3 and 4, where we have 3 point, let's say 3.5, and we have like 3.7, and then we have 4. So we deal with like these values, but ignore everything else. I hope that makes sense. And again, embedded is okay. I'll use the modern AI technology to explain this because it will be more relevant and easy to understand. Embedded is where you take like a lot of data, right? And you assign it a role based on how it interacts with every other data in the data set. So, for example, when we do NLP, we have some filler words. We have is, of, the. These words do not carry meaning in itself. These are support words, right? They support other words. So if they exist in our data set and we just assign it, let's say normal weights, right? Which word are most frequent? If I train a model on which word are more frequent, our model will get so biased that it will only output is of the is of the is of the, right? We need to remove those. We do not want those. And when we embed it, like when we convert it to numbers, this we know that okay, these words with extremely high numbers are not our ideal data. We remove those extremely high numbers and we keep it in the right range. So we know this, okay, this frequency, like most of our words have frequency of 100 or 150 in the data set, but there are three words with a frequency of 3000. So we know that those are helper words and they are not necessary for our data, and we remove that. So this is embedded. Again, these are nuanced topics, and I would appreciate if you went on and read about it on your own. So do we have other questions or can we move on? Let me check.
So we have one more question by Ruchika. Is that how do we choose the right ML algorithm for a particular problem?
Yes, very nice question. I think this question should come to every ML studying practitioner whenever they start. It was a pain for me in the beginning when I was learning machine learning. It was during COVID. I was logged in the home and I was learning machine learning like 8 hours every day. It's a it's a function of time spent with machine learning. So the more time you spend, the more intuition you build with what will. So if you ask me and you showed me data, there have been instances, by the way, where some client is paying me a lot of money, right? And I have to convince them, please do not use this model. Please let me use this model because this is the right model. They're, no, I want the most powerful model out there. I want OpenAI's GPT-4. And I'm telling them, no, you don't need OpenAI's GPT-4. You can use linear regression to solve this. Trust me. So this is a function of how much time you have spent with a certain something, right? But in the beginning, how to do it? In the beginning, you have to read two things. You have to read data characteristics, which is called EDA, exploratory data analytics, right? And the second thing is model characteristics, which I think I'll take another session like on 2nd August where I'll talk about dysenteries, KNN and stuff, where I'll explain the mathematics behind these models. I'll go deep into mathematics. There I will explain properly what does model characteristics means. But for example, let's say linear regression, when you think about linear regression, you know its equation of the line y equals to mx plus c, right? You know it has to be a line, it has to have a slope, it has to have a point on the on the graph. So you know what its characteristics are. Now, if you looked at your data, you plotted your data, you are doing EDA, basic EDA, you plot your data, and your data has a sine function. It's this, right? You know that your linear regression is not the right model for it, right? You will think about, but you know what would be a right model for it? A model with a polynomial model with multiple variables, right? Maybe even three variables would work with a sine wave, right? So that is how you would try to find the right algorithm. I would suggest to just read upon some models and datasets. For example, this is common consensus that on tabular data, boosted algorithms like XGBoost and LightGBM performs the best. On time series data, models like LSTM called long short-term memory, performs the best. Time series data in the sense the data which has a regular time interval, right? For example, weather data, for example, news data, stuff like that, which has regular time intervals. So with those, time LSTM will work well. With data with hidden features like images, neural networks works the best. So this is there are some general concessions by the industry. Experts have told us already, oh, you're dealing with tabular data, use XGBoost. But always when you're a beginner, try all the models. These models are not costly to run. Decision tree, SVM, KNN, these are all classification algorithms, and you can just run all of them and see which one performs better. And then you can go back to your EDA step and then correlate. Okay, for this type of data, decision tree performed better than KNN. And for another model, you can be like, okay, for this type of data, KNN performed better than decision tree. That is how you will make this intuition of yourself. This is what we data scientists get paid for, right? Algorithms are easy to write. Like it's a function call in Python, right? This intuition is what you get paid for, especially in the context of the data and the model and whatever business outcome the clients want, right? That is what the pay us for. So this you have to build with practice. There is no other way. There are no shortcuts. At least in my humble opinion, there are no shortcuts. I have put years and years of work into this to get to this mediocre stage, right? So, no more questions.
No more questions. We can move ahead.
Yeah, let's talk about the meme, right? Uh, so this is bias variance trade-off. This has to be. Let's first start with the fact that this has to be balanced. Like Thanos said, it has to be perfectly balanced, like all things should be. So, what does it mean though? What even is bias? What even is bias? So, if the model generalizes more than necessary, we call it as high bias, right? If we have high bias, it's called an underfitting model, which is bad. So, if you have a model which is not that complicated, the model is not that complex, or the model is not suitable for the type of data, what will happen is the model will generalize way too much. It will not look at the specifics of the data set. It will not look at the nuanced parts of the data, nuanced features of the data. It will just be like, oh, this looks like some form of regular data. So I'll just draw a line, straight line. But in reality, it was a regular data, but it was something like, let's say, seasons, where it goes up and then it goes down. It's not a perfect sine function, right? But it goes like 0 to 100 and then comes back to 0 and then goes to 100 again and then comes back. It does not go to minus 100. So it's a type of data which this model will fail to capture, right? And if you try to fit a simple model on this type of data, it will create an underfitting model. Underfitting means it does not, it underfits, right? And if your model is underfitting, it will just not perform good. It will not perform good in either test or train set. Even during training, you will see bad losses, and during testing or validation, you will see bad losses. So you know that your model is underfitting. What is variance? Variance is the opposite of this. If your model is too sensitive, right? If your model is like, oh, there's like zero point 0.1 difference, I will calculate that difference as well and use that in my a prediction. And if your model is if your model has high variance, it's called an overfitting model. And the overfitting model is sneaky, because when you train overfitting models, it will perform very good on the training set. It will look almost as if it's perfect on the training set, right? But it will perform poorly on the test set. It means that your model has learned, because it's so complex, it has by hearted, memorized the content of your training set. But as soon as you give it data which does not exist in the training set, it will completely fumble it and just underperform, right? High bias or high variance, both of these are not good, right? And this is called the trade-off, right? So what is the trade-off? What is the trade-off? For a good model, we need to achieve a balance where both bias and variance is low enough to keep the total error low. Now, this total error, it's official term, and I'll explain down below what total error is, how to calculate it, and stuff like that. But the right way to train a model is to keep its total error low all the time. And that's why when you do some kind of training, you split the dataset into. I don't know if you have learned this, but if you do some kind of model training, especially for simpler algorithms or algorithms with like which has the risk of high variance, high bias, you will do something called as train test validation. You will divide the data set into three parts: train, test, and validation. Not just two parts. People think it's two parts, train and test. I also do train and test most of the time. So you can just take a subset from the test as a validation data set. But validation is what runs during training every cycle. So you know that your validation still has to be right compared to, and I'll explain all of this with code and graph later in this session. So it will make more sense there. But the point is we have to keep our total error low when we train a model, right? So we have to counter two problems, which is overfitting and underfitting. Oh, never mind, overfitting and underfitting, right? So if you have low bias, right? So basically, your model will not generalize, but high bias, it means it is very sensitive. You have overfitting. It will take every point, every data, and it will remember all of it, and it will think that okay, this is all the data in the world, and it will, do that. The other is when you have high bias. So it's a general model. It's like I don't care about the details, and it's low variance. So again, it's not sensitive at all. It is underfitting. It will not look at your data. It will just be a normal function. It will just give you 0 or 1. It will not give you like 0.7, which might be the right answer in the scenario, right? So anybody knows what MSE is? MSE. MSE is. I'll wait for somebody to type the answer in the chat. I'll open the chat and yeah. Anybody knows what MSE is? If we use an algorithm, a regression algorithm specifically, like linear regression and stuff like that, we have to measure its performance and we do it using loss functions. And MSE is one of the most popular loss functions to exist. Even in the world of AI today, we use MSEs in some of the larger algorithms. Uh, MSE stands for mean squared error, right? It's the error squared and we take the mean of all the errors of the data set. So that is called MSE. So MSE is very common. We use it all the time. This is the MSE formula, right? So we take the prediction output, which is my model's prediction, and we take the real output because it's supervised learning and we know what the real output is. We take its difference and then square it to get the MSE, right? Now, if you consider our real output is Y and our input is X, so real output that we already have, right answer is Y, and our question is X. The relationship between input and output can be represented using output equals to some function of X plus epsilon. Here, this E term, epsilon term is the noise. It's called, it's a noise which exists in all form of real world data. Remember, it's impossible to have data which is not noisy in real world. It's impossible, absolutely impossible. You will always have noise in real world data, right? So you have this noise in real world data, and how does it relate to our context? So if you assume that the mean for the noise is 0, and we assume mean for noise 0 usually because we cannot, let's be honest, if we are very advanced and we try and invest a lot of time in it, we can try and measure it and it will be, some number. But in most of real world data, the mean for the error will be 0 because errors will not have a certain pattern, right? For example, let's take about how most data is collected. Most data is collected in forms of surveys for humans. Humans are sent a form, they are made to sit in a hall and write survey, feedback forms by humans. And us humans, are lazy. We don't like to do stuff. So it's almost always that we will leave some field empty. We will fill some field out of just fun, right? Maybe some guy filled pregnant yes because they were I don't know trying to be funny, right? It will happen, and it's to be expected. So in this case, we just assume the mean to be zero, and that is the case in almost every real world noise where the mean of the noise is zero. So if the mean of the noise is zero, now the only thing we have to deal with is the variance of the noise. And here the variance is different. It's not the variance of bias variance trade-off, is the standard deviation of the noise. So how far apart two noise values are. Let's say somebody filled this noise in my square footage area data. So right, it's 13,000 feet, and then it's 600 feet, and suddenly there are like 3 feet, right? So this 3 feet is noise, and somebody else has filled which is like 2 feet. So we take 3, 2, and there's like 1 feet error. This one is our variance, right? So we take this variance as the square root of the irreducible error. So if you square it, again, a lot of mathematics, why it's done, there's like you can go and read about it. It's not important for most things. Most companies will not ask you this. You don't need this to practice. Just remember that there is noise in every real world data. The mean is zero. So because the mean is zero, we assume that its standard deviation is rho square, right? Which is this term or whatever. This term is called the irreducible error. Irreducible because we cannot remove this error. It exists and it's a reality. We have to live with the fact that this error exists in this data, right? And now the formula for total error, the term total error is this: bias square plus variance plus the irreducible error. This is the formula. And every time you train a model, you plot this. You plot the total error, and your goal is to bring the total error down and down and down. That is your goal, right? So for this, by the way, we can calculate bias as this. So bias for predicted values equals to the average of predicted minus the actual value. So we take average of all the prediction and actual values of that one training run, and it's the bias of the prediction, right? And variance for that predicted value is again average of one prediction minus average of prediction squared. Now, this formula might seem weird at first, right? But when you write it down while looking at a data set, and we will do it by the way, you will understand what this means, right? But I know this is all confusing. The trade-off part, I know this is confusing to even me, right? I know it's confusing. It will all be clear with this diagram, right? Again, I think this is a diagram by IBM. They came up with it. IBM comes up with a lot of cool stuff. So this first board is what I want. It's a dart board, right? You throw darts. Uh, this first board on the top left corner is what we want. We have low bias, low variance. Because we have low bias, the data is free to go to the right place, right? It will not go to like one certain place. It will go to the right place, wherever the right place might be. For in this scenario, it's in the middle. It's the bullseye, right? And we have low variance. It means the data is not to spread out, it's together. So low bias ensures that it goes to the right place, and low variance ensures that it's not too spread out. So it's like in the right area. If you think about low bias and high variance, so here the data is free to go to the right place. And right, you can see some of the data is in the bullseye, right? It's there. But because the variance is so high, some of them completely misses the point and goes, other places, right? Again, this is overfitting. When you have high variance, this is overfitting. It's very sensitive. It goes to like every data. It's like average of every throw. Not good. If you have low variance, means the data is not spread out, but it high bias. It means it's biased towards one certain reason. Here it's biased towards the blue strip. It will always go to the blue strip, right? Not good. And if you have both high variance and high bias, which is the worst, you will have this kind of, it will just all over the place, no pattern, nothing, right? We want this. We want low bias, low variance. And to do this, to do that, this is how we deal with the trade-off, right? So this is called the optimal valley. By this image I just picked off of internet. I don't know where it comes from, so I don't know if it's copyrighted, but anyways, this is called the optimal valley, right? You plot the bias square and you plot the variance, right? And you find this plot, which is total error. Again, we know the formula of total error from here, right? Remember, there can be very low bias variance or very low bias, and that might not be our optimal value. Our optimal value is where both of these are low enough, not the lowest, low enough to get us total error as the minimum. And here the total error will be minimum, right? At this point in the optimal value. So this is a bias variance trade-off. I think we have about 8-9 minutes. So before I take any questions, I would like to demonstrate this thing, basically bias variance trade-off, because I think it's the right way to explain to clear all the confusion. And I'll open Colab, right? I'll open a Colab tab. So yeah, this is my Colab tab visible to
Yes, it is, sir.
this, right? So I'll just write a quick code. It's a dummy code. It's not a real, real project. I wish we had time for real project, but we don't. Uh, so this is again standard libraries, NumPy, Matplotlib, PyPlot. Here I'm generating a synthetic data where the data has a sine nature to it, and because real world always has noise, so I will always also have noise with the data, right? Because noise is necessary for the functioning of our algorithm to witness how it works. So I'll just run it and hope that it runs. So okay, this works. So let's now here this is the range of, if we have this equals to 1, degree equals to 1, it means it's a linear regression. It's a single degree polynomial, right? Now I want to test polynomials from the degree of 1 to 8. So I want polynomial with a single degree, I want second degree polynomial, third degree, and as the degree of a polynomial increases, the complexity of this function will increase. It means there are more variables for the model to change, right? The model will have more variables for the training to change. We'll keep mean scores, this, all that, right? This polyregression. So sklearn, which is this scikit-learn, it comes with very handy function called this, right? Linear regression. And here we can choose how many degrees of polynomial we want for the linear regression. The more degrees we'll have, the more versatile it will be, the more it will try to fit to the data more, right? So I'll just go through, because most of things happen here. I created a model, and this is a for loop where we go from 1 to 8, right? So we'll go 1 to 7 because we don't consider the eighth element in Python, right? Python, you have 1 to n minus 1, right? So we'll go to 1 to 7. And here, let's say we have a pipeline where we know we have to use linear regression, and then we have polynomial features of degree n. So if n equals to 1, our polynomial features will have degree 1. So one feature. If we have n equals to 2, we will have two features. If we will have more degree, we have more features for the linear regression model. Now our scores, we have cross validation score. Cross validation is nothing but here in Python, scikit-learn has implemented Remember, I told you we need to divide our data into three parts: train, test, and validate. Here, scikit-learn will do it for us. It will every time it will create a separate validation set and a separate training set and cross-validate. So it will use different validation data every time. If you use the same validation data every time, your model might try to fit with that validation data, right? So we change the validation data every time. Uh, so that's what we do here. Cross validation equals to three. It means we try to validate with like three types of data. And here we have negative mean squared error. This is the scoring we are using. Now, we choose to use negative mean squaring error. There are other ways. There is RMSE, root mean square error, and a lot of other ways. Negative mean square error just gives us a sense that it's a loss because it's a loss function, right? We don't want it to have positive values, and there are other reasons for it, but this is just convenient for our use case, right? Uh, so what happens is we just keep all the mean scores, we save it because later we're going to print it, plot it to see. And this is the important step. This two words is what trains the model, right? So this is our model polyjeg, and we fit x comma y, x and y are our data set, and run the models because we have to save it. Append means we keep it in the list, so we save it so that we can plot it later, right? I'll just run it and hope that I would have gone in more detail for the code, but sadly we don't have too much time, so I'm sorry about rushing it, right? But it's simple. You can generate it using AI also if you want. I would suggest if you're learning something, don't use AI during you learn. Use it to evaluate. Use it to, for example, you have built something and you ask it, how can I improve it further? How can I make it better? Right? Stuff like that. So, okay, we have already trained and stored all the data we need. Now comes the plotting part, right? So first we need to find the optimal degree. Here, NumPy has a function, handy function for it's called argmin. Argmin means argument minimum. It means for our mean scores, we will take whichever is the minimum value because we want, remember, we want the lowest possible total error, right? So this is our minimum, and optimal error will be the minimum of this mean scores, right? So now we want this valley, optimal valley, and because for it to actually make sense, first we will plot the data set to see how the data set is as it is, right? Like we need to absolutely look at the data set, how the data set looks. So let's go. This will take, yeah. So this is our data set. The points are the data points, right? Uh, as a human, we can tell that it has like this sort of it's a part of a sine function. If I increase the sample size of the data set, which I will do shortly, you will see a proper sine function. And the green line here, can people see the green line? I'm afraid it's not visible. Is it visible?
Yeah, yeah,
There's a
it is.
green line here, and it's the real function. So I just plotted a sine function to show what we want. And the red one is R for our model, right? So when degree is 1, we have a linear regression. Voila, right? So we have a straight line. When degree is 2, it's slightly curved. So for this data, this might look like the right fit. But from the green line, we know this is not the right fit. We want a sine function. But when we take degree equal to 3, we can see that it's kind of the right function, right? And if we take degree equals to 4, we think it's overfitting now because now it's like almost imitating the data, which is not good. What if next the data is like different? So MSA is 0.39 here when degree is 3. So if I did things right, I think that is what we should get as our answer, right? So let's find the best fitting model. Best fitting model would be uh, right, degree equals to 3 and MSE is 0.397. What we are doing here, again, We are running it with every degree. We are saving the loss function from every training run, and we are plotting it against our data set to see which. Now here, because we know already that our data is sine function, we have the green line. In real life data, you will not have the green line, right? You will have to look at the data like this plot without the green line, the blue color plot, and find which distribution it is from. Like, is it a bell curve? It is a whatever, right? What is the distribution it is on? And try to figure out if your model fits right. This will come with practice. There is absolutely no hack about it. You will, the more and more projects you will build, you will have more and more experience about how to deal with this. So this here is the best fitting model, and just to make it more clear, I will copy paste the code for the trade-off to see what the trade-off looks like, right? So I'll plot it. This is a simpler data set, so that so it's not that much visible, but you can kind of understand what's happening here. So here you have bias variance being plotted as total error, and this is total error because our values are so far apart. And again, scaling, I should have done some scaling here, but because our values are so far apart, this is it looks like almost a flat line. It's not. These are different values in the range of 0 to 10, let's say. And here we got our optimal value. But if you see, as we proceed, you see that the standard deviation of the error goes very high. It means as we go further, the variance of the model is going very high, right? As we are low, our standard deviation is the minimum. It means our bias is very high. So this is high bias on the leftmost part of the graph, and this is high variance on the rightmost part of the graph. And somewhere in between, you have your optimal valley, right? If I did not use a large data set, because if I use a large data set, it will take a long time to run. So let's try 5,000 samples, and irreducible error is 5. Yeah, it's fine. So let's try this. All right. Here, see, our degree has increased. So now a more complex model fits it better because now we have more data. It's generalizing better, and here we can see if I can I zoom in. If you see closely in the graph, and do this yourself, by the way, please do this yourself. If you want, I'll just share a link to like this collab notebook. This here it's like slightly above 0, right? And as it goes further at 3, it has come down to like near 0. So it's like 0 point something. I hope. Let's check what is for 3. It's 0.6, right? And for 4 again it's 1, and then for 5 it's 0.3. So this is right. Here at degree 4, our model is kind of this is how we basically find the bias variance trade-off, and this is how we visualize it. So here we know that you have like high variance on the right side, high bias on the left side, and yeah, this is how we find out bias variance trade-off. So I think this covers everything I wanted to talk about in this session, right? We talked about feature engineering, feature selection. We talked about bias variance and bias variance trade-off. All of these topics are very necessary. I was told to actually cover algorithms first, descent trees and SVM and KNN first, but I choose to do this because this is important. Once you know this, and then in the next session when I explain algorithms, like what is this algorithm and why are we choosing this algorithm, these concepts will come in handy, and that's the reason I decided to go with these concepts first. So if there are any questions, let's take those. If not, then I think we can we can
Yeah,
conclude this session.
as I see there are no questions, so we'll end the session here. So okay, that brings us to the end of today's session. Thank you so much, Akshay sir, for joining with us today. What a wonderful and insightful session it was. So stay curious, keep building, and we'll see you in the next session. Until then, keep learning. Thank you, guys.
Thank you. Bye bye.